and today I will conclude the part on AI explainability. So for the one of you that were not at the lecture on Wednesday, this is basically what we saw in the last episode. So I introduced you explainable AI concept. The idea is I trained my machine learning, my data mining model, and now I have no idea of how basically this model works. So when I use the model, I'm not able to explain why this model is predicting what it's actually predicting. I'm not able to give an overview of any kind of understanding about the problem I actually modeled with my predictor. So this is, in some field, is not a problem, but in general is something important. And so what I'm basically presenting you here is this new emerging field that is explainability, interpretable AI. And the goal here is basically, in particular, I'm focusing on some techniques that allows you not actually to create a model that can be easily analyzed, that can be easily interpreted. But the focus here is, given that your model is a black box, so even if you use any kind of model that we know that are difficult to explain, like random forest, even worse, super vector machine or deep neural network, I want to have some techniques that allows me to explain after the model is trained how the model works, and for how the model works we mean two things: how the model works in general, so which kind of general concept the model learned about the data, and how the model works specifically for my specific prediction. So I have a prediction, and I want to know why this prediction, how this prediction actually was done. That was basically the idea. So the first things I showed you Wednesday was this feature importance, permutation importance metric that is basically a way to compute rank your is a way of ranking your features based on how important they are in your model. So for considering how your model works, how important is each one of the features you have for doing a prediction. So this was basically the idea, and we saw a couple of examples, a classification problem and a regression problem. What I'm showing you today, the first things I want to show you is another thing. It's another quite simple approach that is called partial dependence plot. So the idea here is that I want actually to not just to have a ranking on the features, so how important the features are, but I want to understand better how actually the change in a feature affects the change of the prediction. So I want to dig more into the relationship between the features, so how the feature change, the values of the feature changes, and how actually the model prediction changes. So I want to find this kind of relationship. This, of course, is obvious if I have a simple model, because if I have a simple model, I just look in the models. If I have some rules, for example, I look at the rules and I get this information. But if the model is a black box, it's too complex, I don't have a way of looking into the model. So this is done again as an approach that is applied later. So first step again is train your model on data. Okay, no worry about how you actually perform, how actually do how good is the performance of the model here. We don't focus on that, and we don't focus on understanding how actually I want to stress this again with respect to, I already said this last time, but I want to stress again. We are not trying to understand the relationship between the features and the actual label in your classification problem, or the actual target if it is a regression problem. What I just want to understand is the relationship between the value of the features in input to your model and the output of your model. If your model is performing poorly, it may be that you learned something wrong that is not actually what is actually going on in the data. And so this method will explain your model, not the data. Okay, so that's a big difference to take in mind. So this stuff came after you have a model you are satisfied with. The only, because I got a few questions at the end of the lecture last time that made me think that this was not probably enough clear. The only thing that probably can get you confusing, that last time I told you that one of the possible approaches of these techniques is also to improve the model. But this is just in this context. If I understand how my model works, I can probably discover something that I was not expecting or I wasn't aware of, and this can give me some idea to go back on my step in the way I created, in the process I used it to create my model, and change the way I create my model and improve this process in order to get a new model that is better. But this is not a direct result of these techniques. These techniques just want to explain your model. So, going back to the partial dependence plot, what I do here is simply train the model, and then I run the model on each sample of my data set. Again, I can do this on a validation, on a separated validation set, on a subset of the training set, on the whole training set. There are very slightly change on that. In general, in principle, I could be more interested in understanding how the model works on a subset of data. And in this case, I can use that subset of data just to explain the model on that subset of data. So, once I selected this data I want to use to do the explainability study, I run my model on each sample on this subset of data, and I basically keep all the value of the features fixed to the value they actually have in the data, except for the target feature or features, because we will see that we can use this plot, this technique to study two features at once. So I have one of two features that I want to study, and for these specific features I will I will apply my model by using different values for that feature. So I will make change. I will create a new sample of data that are not actually in the original data set. I will be created basically keeping the sample as it is and just changing one of the feature values that is the one I want to study. At this point, I apply the model, I get the prediction, and I will get several predictions for each possible value of my feature, and I will simply plot the mean and maybe the confidence interval of the output of my model. So, just to make it simple with an example, suppose that my model is a function. I have x1, x2, x3. So these are my features. So I will have a data set with some value for this. I run into each one of these. Suppose that I want to study how is the relationship between the input, the value of x1 and the output of my model. I will keep 3 and 6 and I will create a new instance with, I will use 1, 3, 6, I will use 2, 3, 6, I will use, let's say I have other values of x1, 7, 3, 6. So I will just create all the possible combination between the part of the sample that is not the one I want to study and all the possible value for the features I want to study. The value that I will use here will be used, can be chosen by a set of values that you decide to use. So you can tell to the model, try study the value you want to use to study the dependence between x1 and the output are x1 equal 1, x1 equal 2, x1 equal 7, because I know that are the relevant value that I want to study. Or otherwise I can just leave it to the algorithm. The algorithm typically will compute this value looking at this. What this typically does, the algorithm is compute an empirical distribution of the value of x1 and will choose a fixed number of values equally distributed along the distribution. So we'll use the percentile of your values distribution. Okay, so is it clear how it works? It's pretty simple. I mean, that's the idea. And what you get, I will show you with an example how it works. For the example, I'm using, I don't know if I put the link somewhere, no, maybe not. It's the library I'm using here is called PDP Box. You can install this PDP Box library. Is on Python index package, Python index package. But the point is that the version that is now installable with PIP is not the last one, and I got some trouble for some changes in Matplotlib when I run the notebook. So what I did in the notebook you will find on GitHub is basically that I just downloaded from GitHub the latest version of this PDP box and I just included that into the notebook. So here is just using the PDP box from the local version I downloaded and included in the directory inside the notebook. You can play around with that, or you can install, or you can also modify the version. It's not extremely difficult code if you look into that. Oh, and one thing for some of you is had downloaded the notebook last time. This is still the same notebook, but I updated it yesterday, so download the latest version because there is some addition at the end. So what I did here is, again, I created a simple decision tree classifier for this man of the match classification problem. This is a very simple problem I introduced last time. Is statistics about soccer matches, and where there was basically two national teams playing together against, and you basically as some statistics, the typical one you have in soccer, so how many goals have been scored by the team, the percentage of possession of the ball, number of corners, etc., etc. And the goal of the problem is predict if that team, the one for which you have the data, has been awarded the man of the match. That is basically a decision taken at the end of the match to say which was the best player of the match. And of course, it is chosen from one of the two teams. And this classification, the class is 1 if it comes from the team for which you have the data, or 0 if it comes from the opponent. So that's basically the classification problem. So I created with scikit-learn a simple decision tree classifier. Actually, I just used some values, not particularly. I did not do any particular study on the values, just to have a simple tree. And I fit the data, the training data, and training output, the training class with this model. So now I have my model, and I want to explain the relationship between the features and my model. We saw from the permutation importance on Wednesday that the number of goals scored by the team was one of the most important features to do the prediction. Now we want to show how is this relationship. So we know that it's important features, but how changing the number of goals scored is actually affecting the output. And this is computed simply by looking at this. You run this, you first create this object that is PDP goals, and you use this function PDP isolate. This function, let me go like this. This function show me requires me to provide the model I want to study, the data to use for do this analysis, so to take the value, to take the sample and change one of the features. The feature I want to study, in this case, is goal score. So goal score is in that example x1. And also requires me to give all the name of the features, so all the name of the column basically. Okay. So this variable came from the code we ran last time with the feature importance. So I want to go back on that. So are basically this information. So what I do now, when I do this, the library already do this calculation for me. Okay. Now in PDP goals, I have all this calculation done for me. So I can get the value from PDP goals from the object, but even more conveniently, I can use this PDP plot function that do a visualization of this information computed for me by the algorithm in a nice way. And in fact, if we run this PDP plot, we got this. This tells me the relationship between the number of goals scored and the actual prediction of the model. Okay. So here I get how is the relationship. Actually, what is actually showing me here is not the prediction output, but is the change in the prediction output. So this is how the output in the prediction change with respect to the value at the leftmost of the graph. So this is basically testing. Keeps as a baseline the value I will get with goal scored 0. And given that as a baseline, this tells me how the prediction change as soon as I change the value of goal scored from 0 to 1, 1.5. This is actually fitted on this point. So these are the values that actually are selected by the algorithm. And the fitted area is simple, the confidence interval. You can change the alpha value for the confidence interval into the code, but this is basically what I get as an idea. So this tells me, for example, quite clearly that the goal scored is actually the model is using the goal scored in a quite simple way. The goal scored by a team increase the probability significantly from 0 to of more than 50%, because this value is around 60%, of having the prediction of the man of the match. However, it also tells me that this change is not increasingly, is not linear, but after one goal scored, I'm actually not getting any more benefit. So that's basically the idea. Okay, that was basically the idea of the approach. If I want to instead to have the actual prediction output instead of the change in the prediction, I can simply add this argument center equal to false. I will just in this notebook demonstrate this with another feature. This is another model, PDB model I did now for another feature that is the distance covered feature. So if you remember, another feature that turned out to be important is how many kilometers were covered running by the players of the team. So this was resulted to be important. So we want to see how this is the relationship between this value, this feature value, and the output. And this is actually the answer. Okay. So it tells me that the baseline is slightly 50%. And this is actually the baseline of the prediction when the distance coverage is not 0 but is at its leftmost value. And again, increasing the distance coverage, I get an increase, but not more after a certain value that is around 100 kilometers approximately. Okay? In this specific case, I use a simple tree because I wanted to make it possible to you to check why these results that can make sense or not are obtained by the algorithm. And to have an idea, you can just simply, with Graphviz, that is a library for plotting graph, you can simply create a visual representation of a decision tree. So with this export Graphviz function, you pass to the function the scikit-learn model of the tree and the name of the features, and you get this nice representation. So this is too big probably to be seen in a single figure, but this is my model, okay? And if you look at the model, you can clearly see how the value of goal affect its performance. You see the goal score is at the top, and you can see that at the very beginning you have a perfect balance of the nodes between 0 and 1, so between not being awarded the man of the match and being awarded. And if you look at the left subtree, when the goal are lower than 0.5, so no goal actually, because the goal of course cannot be with the fractional part. You see that now the distribution drops down to 24, 0, so no man of the match, and only 2. So the probability, the chance that I'm going to predict yes, I'm receiving the man of the match are dropping down, and this is actually why you get this difference. Okay? And another thing about instead the distance covered is described here. Here you see where the 100 values come from. Okay? So this was just not to make it clear. This was just to let you see more in a more transparent way how this thing works. This is not actually what you will do in the real world. So in the real world, if you have a model like this, you don't necessarily need to create that. Actually, this is a very compact representation, can be still useful. But if you have this model can be explained. You can look into the model. But this becomes, these techniques with the plotting becomes more interesting and more useful when you don't have a very simple model. Suppose that now I have a random forest with 100 trees. So here I have my stuff and I feed this with my train data again. This now is a random forest model. It's more complex. Now I can do the same analysis and probably I hope to get data that is not so much different because even the simple model was trying to capture something, but probably I will get more details, something more interesting. So that's basically the idea. So again, I rerun the PDP, this is the distance one, the distance covered one. I again rerun the PDP isolate model for the distance covered. And these times I also added this plot points distance equal to true, and I will get to that in a moment. So this is the results. And now I get some slightly more complex behavior. Again, I have an increase after 100, just at 100 kilometers. But then it also tells me that after a given amount of kilometers is not more so relevant. It's even it's not only not so relevant to add kilometers, but can even lower a little bit my probability. So here you see. Now the scale is is not extremely good here. Just a side note, except for one library I will present you, most of these libraries are rather nice for the functionality they offer you, but I really don't like very much how is done the visualization. So my suggestion is, and I use that for brevity here, but my suggestion is if you actually want to use that in real world, you might want to create your own visualization. So just use the library to compute the numbers and then do any visualization, use any visualization library you have out there. There are very nice visualization libraries, Seaborn, Matplotlib, Plotly, whatever you might have seen that allows you to create very, very good visualizations. So even you can modify this code and change the visualization part of this code to make it more suitable to your purpose. So in this case, I see here that there is an increase and there is a small decrease. These times, however, I have also the distribution of data points here. This is done with the RAG lines. RAG lines are typically the small vertical bar. I put for each data point I have for that value of the axis. Why this is important? I suggest you, when you do this plot, to always add these. I didn't add them in the first example, but when you do it for real, add them. Why that? Because if you don't have data points, what you see on the screen, or if you have too few data points, what you see on the screen is not so relevant. So of course, if you don't have data points, you cannot expect to get meaningful results from that. Maybe it can be also a part of the space that is not actually relevant in the real world, because maybe there are no real sample in the real world that have value in that very specific area of the space. So this is give you an idea of how confident you can be on what you see from the plot. So extrapolating the output of a prediction model is not always a good idea, especially for area of the space where you don't have samples, real samples. So keep that in mind. I will move that to the, here is where I put the link to the library. Here I will move to a more, slightly more interesting problem, the regression problem by rental. That I already used the last time was basically a bicycle rental company that rented bicycle in Washington DC, and you want to study how it's possible to predict the number of rented bicycles based on the weather condition information. And so what you basically are going to do here is applying the same approach to this regression problem. So if you remember, our feature importance analysis told us that temperature and humidity were among the most important variables to predict this number of rented bicycles. And here I created this isolated model, and I created them to study the relationship between temperature and the number of bicycles that was actually rented. The model, I didn't create again the model. The model was trained before, and was the bike forest model, is a random forest with 100, if I remember correctly, trees. Was trained before, so you don't need to train it again. And you run the plot, so the PDP plot, and on my object, and this is the rather nice relationship I find. There is this increase of the number of the bicycle rented with only a slightly decrease at the end of the interval, but very slightly. Okay, so you might expect from this a slightly different behavior, because in principle you could expect that, of course, when it's extremely cold, I probably am not so keen to moving by bicycle, but even if it's too hot, maybe. This instead is suggesting that the cold temperature is much more critical with respect to the high temperature, at least according to the model. I can also do another analysis, same analysis with the wind speed, and this is show me a small effect, because again you see here is the number of bicycles rented per day. So in this case started from less than 4,000 when it's extremely cold to more than 5,000 when it is extremely hot. Here the difference is much more small, but still there is this effect, and I see exactly this is what you would expect in real life. the more windy is the day, the lower the probability I will get a bicycle. Quite obvious. And the model actually is behaving like that. So now what I'm telling you can be seen in a way of improving. If I get something really strange, for example, if I would get the opposite in the temperature model, so the opposite behavior for what I expect from my common knowledge about the relationship between the model and the temperature, I could probably want to dig more into what's actually happening. Even if the performance is good, maybe there is some mistake I made in some point. So in that case, these techniques can be also used for debugging and improving your model. Otherwise, you can just use them to explain your model and that's it. So you are satisfied with the model, you are confident that your model is good, but then you go from to the rental bicycle that hired you to do this data mining model for them, and then you present them the model and also explain them the model with this. Because otherwise you just have a black box and say, this is the model, trust the model and don't ask why it's working. Or at least I can provide you a table that show you that my analysis show that this model is accurate, that will perform will generalize well, but still is a table of numbers. This is much more easy to understand, especially if you have people that is not expert in the field, is not technical people that you can discuss with the actual metrics and about metrics and numbers. And the same analysis for humidity, in some sense, tells me why probably I don't see in the model a high decrease for the highest temperature. I don't see any strong decrease when there is an higher temperature, and this is probably because the model deals with that situation with the humidity value. So what is actually probably extremely not comfortable if you think it depends on the region of the world, of course, but Washington DC is in some sense similar to Milan, for example, to some extent. So what is really what is really a discomfort is not just the high temperature per se, because we don't reach, for example, in Milan usually more than 40 degrees. What is actually really a discomfort is the highest humidity you get in summer. So if the humidity is extremely high, you get a sensible decrease. And this is actually completely meaningful with what you expect in the real world. You see also that I also plot in this plot there is another thing on the bottom, and this is achieved with this parameter x quantile equal true, and this is just instead of plotting the RAG, you can also show the quantile of the distribution of the feature. So here I see the all the quantile intervals of my feature distribution. And that's actually rather nice. If you do that, however, you see that now the scale of the x-axis is completely distorted. You see that the size of the interval 0 to 0.47 is equal as the same length of the size of the interval from 0.47 to 0.54. Instead, in this case, these were scaled as expected. It depends, it's up to you. Personally, I don't like very much when you introduce some distortion in the data, when you visualize the data, because I think that you never know how people actually perceive the data with a strange scale like this that is not uniform. So my personal preference is this, and if you really want to show this quantile or distribution, you probably should do a separated plot of the distribution function of the value of your feature. That's my take on that. But I just wanted to present you as something that is offered by the library. Question?
I wonder if this kind of approach can make sense also with neural networks on when we use, for example, kernel function, and we just increase the dimension of our problem without really having the control of this transformation.
Actually, the point is, it makes sense as soon as it depends on how you generate the sample data to do this transformation.
So, the sampling feature actually disappear inside the neural network since there is a combination.
Yeah, of course. But the point is that the features through the layers are actually processed and mapped to actually, in some sense, mapped to a different space. That's true. But the point is, if you look at a black box model, if you look at any model, if you look at the model as a black box model, what you really care is the relationship between input and output. You don't care actually. The point of this is actually that you don't want to care about what actually is going into the model. The things I was telling you about the distribution of data is if of course you know that your model is applying some kernel function, so works generalized only locally. Let's say, for example, more than a neural network, I was thinking, let's consider a supervector machine where you have kernel function that may be a strong local generalization, but with parameters that makes generalization very, very poorly as values move from the data point. Of course, if you have a sparse training data set and you use this approach, and the value of the feature you use in this approach is a uniformly distributed value of the points on the space, on the range, you know that you are sampling the output, you are asking to your model to predict an output in large area of the space, for which you know that the model won't be able to generalize. You know because you know how the model works. Okay? So in that sense, if you have, I'm not saying that you have, you can look into the model so you have a gray box model, so something that is not white box but still you can understand something. But I mean, if you know how the model works and you know how you did your stuff, you probably can understand what is a good idea or not. But still, if I show you the distribution here, you still will probably see that the points here falls in region where there are no data points, and so you should expect that you should take this value in that area between really with a pinch of salt. I mean, it's not so relevant. So in that sense, you might want to look into that. But otherwise, you are just care about the relationship between input and output. And actually, this is actually what matters for explainability. Because explainability means I want to explain how that model create its prediction in the real world with the real data, I don't care if it maps into a multi-dimensional space, because at the very end you need to explain to some people why your model took some decision based on the actual data, and that's actually you are trying. So in this sense, you are not mimicking with these techniques the process, the actual process that they use the model. You are creating a completely new way, and it's possible that the explanation you came with these techniques does not really reflect the way the model works. Okay, so you might find an explanation to a model that is actually different from the way the model actually works. Is this good or bad? It depends. If your goal is model debugging and improving, it's probably bad. If your goal is explainability, it's fine. My goal is explaining you how this model takes decision, and I do carefully on that. In that sense, using a validation set for doing explanation could be better than using the training data set. If you care just to use, if your goal is actually find an explanation that can generalize well when you will use the model in the real world. Okay. About this specific topic, however, at the very end of the notebook, I put a couple of references, in particular to a book that you find on GitHub, so it's free. It's a very nice book that covers this topic and much more. It's more comprehensive, and there is a long introduction on what means actual explainability, and also discuss this trade-off between. I want really to explain exactly what is the process the model is using for the prediction, or I'm just care about explaining the relationship between the input and the output. Okay. If you have a categorical or something that is more similar to a categorical value, in this case there was the season. The season was 4 values: spring, summer, fall, and winter. They are numerical value, but actually this is, by the way, a categorical feature in strict sense. So if I want to show the same approach for that, I'm not recommending you to use the PDP plot function, because this gives you a completely wrong perception of what's going on. Because you have 4 different values that are not actually a quantitative value, so you show some sort of trend in something that has no trend meaningfully associated to that. So in that case, what I suggest you to do is do like here. You basically run your PDP isolate. You create your PDP isolate object again with the model, with the data set, with the feature's name, with the feature you want to study, and this is the number of points to use for the grid for doing this change in the feature value. And then you don't use the PDP plot, but you get the PDP values that are actually the value, the mean, confidence, whatever, and you can just plot them in the way you want. I suggest for categorical values a bar plot. So in this case, I just use a bar plot from Matplotlib. So I definitely suggest this. This is much more meaningful as from a perception point of view. You can run this also from for a couple of features. So if you want to study two features at once, so you want to see if there is, which is the relationship between two features changing, so you want to study how two features interact together to get your final output. You can use, instead of the isolate PDP isolate object, the PDP interact object that has similar argument, but instead of just one feature, you have the two features and array with the name of the two features you want to study. And then you have this PDP interact plot, and this can be created with the contour type plot. So this is fitting the distribution with the line, and so this gives you the idea. So in this case, I know that humidity and temperature interact in this way. So you see that temperature, this is basically what we already know from the isolate analysis, but in this case you see more clearly how is the interaction. So the number of bicycles is still like increase with the temperature, so there is a gradient when the humidity is medium low, there is a gradient, a positive gradient that made increasing the number of bicycles, but as soon as the humidity approaches a very high value, even if the temperature increases, of course the number of bicycles is not increasing anymore because it's too hot, too humid. And also here you see this sweet spot that is the highest prediction of the model, where you have a mild temperature, not too hot and not cold, and medium humidity. So this is the sweet spot that is the best weather according to the model for renting a bicycle. The same plot can be achieved as a grid plot, and in this case you don't anymore fit the contour, but you just have this heat map with the grid. As you see, the visualization is not perfect in this case. For example, this is not fitting the box, so you probably need to do some matplotlib work on that figure to get the results you want, but still is a nice starting point to have the results. And the data is actually the same. In this case, there is the x quantile equal to true, so this is actually uniformly created for the quantile. So there is a slight distortion with respect to that. I honestly again prefer this one. I think it's more informative than this one. So, good things and bad things. This is nice. The only problem is that you can analyze at max two features at once. I recommend to always keep the distribution of the data in the plot, as I told you, to avoid any misleading perception in the user. There is an underlying assumption in that, and the underlying assumption is you assume that the effect can be isolated, so there is no correlation actually. So in this case you assume that these interact together, but the other features are not so strongly correlated with that. And the same here. You assume that you can isolate the effect of this feature in the model, and maybe it's not the case. And of course this is an average. So there might you show the average effect. So there might be point, even if I show you the confidence interval, I don't capture the fact that I might have behavior completely opposite that provide me an average that is not meaningful. Because here I saw this, but I might have only lines that are on the top of the confidence interval, lines that are at the bottom, so, or some stuff that keep crossing, and I see the average and I don't get what's going on inside this band. If I want to do that, I can solve this. I can use this approach that is individual conditional expectation. It's the same thing, but instead of doing the average for all the data set, I just plot one line for each sample I create with this approach. So I do the same thing, but instead of generating all this plot and do the prediction for all of them and average the prediction and computing the confidence interval of this average, I just plot the prediction value for this, and for this, and I get a line for this one, and that's basically it. And to do that, I don't need an additional library, even if this approach has a different name in the literature. Actually, the computation you have to do is the same, so the library do both this approach. And to get them, you just have to add to the plot function plot lines equal true, and that's it. And this is the result for the temperature. In this case, I don't have strange effects, so in this case, the isolated model was working well, but in some case, but still you see here there are some strange behavior here. The dynamic is slightly more complex. Suggests me that it's probably not so easy to get. And this is probably because I suspect in this case, for example, that there is some interaction with the temperature when I'm looking to the humidity that is not completely captured if I look at the humidity alone. And so in the highest part there is this strong, there is this slightly crossing of line that doesn't allow me to get everything straight. This is the temperature effect. This is not anymore, this is the centered version, so this is the change, the temperature increase makes on the prediction. So here you see very well that the baseline again is the leftmost, so this is the baseline, and when the temperature increases, the number of rented bytes increase, and increase a lot, because the daily increase goes up to 2,000 more bicycles rented, and the average is around 4,000, so from 4,000 to 6,000 actually, and then it's basically stay constant after some level with a slightly decrease of the value, and the same for humidity. So the last things I will show you, because I have another things, but I will just leave in the notebook to you to check if you want. But the last things I want to instead present you is the Shapley additive explanation, or SHAP. These Shapley values are basically techniques, are an approach to try to instead break down any prediction in a way that for any prediction I'm able to tell you which contribution each feature add in this prediction. So in this case, for example, suppose that I give you an instance of a day with temperature, humidity, wind speed, whatever, and I want to know, and I predict that for that specific day my model say there will be 5,000 rented bicycles. So I want to know exactly the contribution of each feature value of that specific instance that created that 5,000 number. Okay, so I want to know which is the with respect to the average to the expected value, to the average value. So the average prediction is 4,000 in that specific model, 4,000 something. If I get 5,000, it means that my model is predicting an increase of 1,000 with respect to the average. So that 1,000 increase, how can I break down that 1,000 for each one of the features? So each one of the features is responsible of a fraction of this 1,000. How can I do this breakdown? Okay, that's basically the idea. If I have a linear model, to understand better this, let's consider a more simple case at the beginning. Suppose that you have a linear model, linear regression model, for example. So I have this equation fx. I have this equation fx. So it's a function of my feature vector x, and I have a weight for each one of the features. So in this case, if I want to tell you which is the for a specific instance, which is the contribution of each feature to that increase, it's extremely simple. I can even compute that in an analytic way, because this is an additive model, and I can do the computation. And this is simply, I know that this is exactly the contribution. So the contribution for that specific value of x, suppose that xi is temperature. So the contribution is the weight of the temperature in the linear model multiplied by exactly the value of the temperature for that specific day, and I just can subtract the weight of the temperature component for the expected average value of the temperature over the whole data set. And that's basically it. So I'm able to compute that analytically. And that's extremely simple. But the point is, if this is not a linear model, if my model is a random forest regressor, if it is a supervector machine, if it is a neural network, how can I achieve that? So Shapley value approach is based on game theory approach that is actually this approach introduced by Shapley in 1953. And the idea is the goal back then was when there was a game with multiple players and you have a payout at the end and you want to understand how to share this payout among the players. You want to see the contribution of each player to this payout. So that's basically the idea. In our specific case, we use this idea and map this to a prediction data mining context. So in this case, the payout is our prediction, or more precisely, the difference between our prediction and the average prediction overall of the model over the whole data set, to be more precise. And my players, and the players are my feature values. So I want to be able to tell you if today I'm predicting an increase with respect to the average of 1,000 bicycles rented, this 1,000, the part of this 1,000 that is due to the fact that today we have 25 degrees is actually 700. So I can explain 700 of this 1,000 increase just for the temperature. Okay, that's basically the idea. How you do that in practice? You need to compute the marginal contribution of each feature with respect to the whole values of the feature. So consider that you cannot really assume that each one of your contribution, each one of your feature is independent, so as an additive effect. You must consider all the possible combination of subset of feature and study which is the contribution of your feature, marginal contribution in that combination. So let me explain in the example of, let's cut down to humidity, temperature, and wind speed. So suppose that today I have wind speed 0 km, humidity 70%, and temperature 25 degrees. So the and I want to study the contribution of temperature. First, I assume they are independent, so I study which is the difference between having 25 degrees and not having 25 degrees. So all the possible variation of all the other parameters randomly. Then I say maybe the fact that I have 25 degrees and 50% of the humidity, it's important. They are linked together. So I also compute the contribution of having 25 degrees and 50% humidity with respect to having 50% humidity and what else ever. Then I say maybe also windy is important. So 50% humidity and wind speed 0 and 25 degrees and all the other possible values for temperature, but still keeping 0 in 0 at wind speed and 50% temperature. And finally, also the other, the remaining combination is just look at wind speed together with temperature and regard the humidity. So the feature you don't consider into the interaction are the ones that can actually can change. So I compute the prediction by keeping fixed some feature value and make all the other change. And I average the prediction for all these possible cases, and I also always make the difference between having my temperature value fixed or having my temperature value random. And all these differences altogether give me the contribution, the marginal contribution of the features. So this is the idea. However, this in practice is almost infeasible because the number of possible combinations is exponential. If I have many features, this is extremely expensive to compute. So there is an approach that is less expensive that do this sampling in a random way. So here is the algorithm, but the idea is the same. So instead of just using all the possible combinations, I just create a random permutation of the features. I select a subset of them, and this is my randomly sampled combination of features that I suppose work together, and I compute the marginal contribution of my feature for that subset of features that are linked together. I repeat these things several times, let's say big M times, and this is the way I compute my contribution. I need to do this for each one of the features, and at the end I have the contribution of each feature to the prediction outcome. Okay? This is done for you by this very nice Chef library. This is probably the best one among the one I'm presenting you. It's very well done, and you have a lot of things. You have this kernel explainer that does this random sampling I just described you, and this is a black box approach, so can work with any model, any black box model. But however, in this library you have also some other explainer that instead can work only with some specific kind of model and leverage the fact that if you have to compute this stuff, if you know how the model works, in some case you can compute the exact value or the approximated value faster. So if there is an explainer that is specific for trees, there is an explainer for deep learning, there are different explainers that leverage on the knowledge of how the actual model works. But for now I'm just presenting you the results with the kernel explainer. This is the more general one. So you create this object shape explainer. You need to pass to the model the prediction function. So if it is a classification problem like the FIFA best man, I just pass the prediction probability object, and that's basically my model, my all things I have to pass. And the training set I need to use for the explanation. Okay? And what I typically get is an object that I can later use to explain the data. The explainer can give me these values. So for presentation simplicity, I put them in a data frame just to let you show. So what I did here, I wanted to predict, to explain, one instance in my data set. So I asked the explainer to give me the shape values only for one instance inside the data set. And this gives me these values. So I know that in that specific case, the prediction, the explainer is can be break down in this way. I can also plot this value more clearly with that, and so I have a bar plot that tells me how these are actually break down by the model. So in this case, goal scored is the one that explains more. There are somewhat negative. What means negative? The negative one are the ones that are decreasing my probability prediction. The positive one are the ones that are explaining the positive change. So that's basically the idea. The library provides you also this very nice visualization that is called force plot, and this shows you the same data visually. So just to explain, this tells me that in this case I have a prediction that is a probability of my model is 70%. So for that instance, my probability to get the man of the match is 70%. But the other interesting thing is that I have, I know that the projector is not very, in this case is not very helping me with the colors, but I see that in the red, the one on the left, I have the feature values that actually are making the probability bigger than the base value. The base value is up there, is 0.49, this is 50%, and these are making them increasing. So the most part of the increase is explained by the goal score and the false committed. The most part of the decrease is explained by the ball possession. Same things can be achieved for the regression. So this is an example of the regression. And you can do even more cool things. One thing you can do is do the same analysis for all the subset of data. And this provides me this string plot that do this same explanation for all the data points. And this is an interactive stuff. So I can order the sample by output value, by similarity, and whatever. And I can also have a summary of the effect of each feature on the whole data set. And this is what I get. So here I see that in this is again the rental bike. The temperature effect is up there. and tells me that when the temperature is high, and you don't see well the color now on the projector, sorry for that, but you see that when the temperature is high, the temperature is responsible for explaining the most part of the increase in the prediction of the rented bicycle. When the temperature is low, is extremely strong the effect of the temperature in explaining the decrease with respect to the baseline. And this can be plotted like this, or can be plotted with a bar plot, or whatever. And this is instead the effect of a single feature on the whole data set. So this is similar to the isolate plot I showed you before, but computed with the shape values. So it's more focused on the distribution, on the contribution, marginal contribution of each feature. So just to conclude, this is a very solid approach with this very solid theoretical framework. It's probably among the explainable approach, the one that has more strong, more solid reliable theoretical framework. In fact, the shape values, the shapely values, has a very nice properties. They are fair in the distribution of the contribution among the feature. They have additivity properties, so they are really really nice from the theoretical point of view. And also, you can really do nice things. For example, you can selecting which are the subset of data you use to compute the shape values. You can also explain not only your model per se, the prediction of your model per se, but you can explain also why the prediction of your model on a single instance differs from a specific subset of features of samples of interest. So this allows you to, for example, if you have, let's say something not, if you have a day, you rent a bicycle, the rental bicycle. If you have a very hot and humid day with a strange prediction, you might want to explain why the prediction of this day is different, not just with respect to the old data, but only with respect to the other hot and humid day. And this will compute, of course, different Shapley values, but will provide you, different values for this kind contrastive explanation. So the only cons, the major cons here is these are very expensive to compute. Okay, that was basically it. At the end, you have the reference I told you before, and if you want, you can also look at the LIME that are the local model, surrogate model. If you want to have a look, it's quite simple and it's at the end of the loop. So that's basically it. Professor Nancy wants to